Hello, my name is Matt Holliday and welcome back to my class. I'd like to start talking about basic types in Go. We'll start with integers and other numbers, and then we'll move on in a little bit. We'll talk about strings, and then we'll talk about some composite types like slices and maps. Okay, before I start talking about some types, I just want to point out a list of keywords and operators, and I'm just putting this up for reference. There's no reason to memorize it. I do want to point out one interesting thing, and that is how few keywords Go actually has. It's another sign about how simple the language is. There are also some built-in types and constants and so on. There's some built-in functions, and this is, again, just a summary list. I won't talk about them all now. Okay, so when I start talking about numbers, what I want to do first is discuss the difference between numbers in some interpreted languages and the way numbers are represented in Go, because it gets to the fundamentals of how the type system works. On the right-hand side of this diagram, I have a picture that represents kind of an interpreted environment. So I have some variable a, I'm going to give it the value 2, so it's going to be treated as a number. And you can think of this, say, in Python. When I do that, what is a? Well, a is not a number in the sense of the computer thinks of a number. A is an object that represents or masquerades as a number in the interpreter. So the interpreter deals with that, and eventually the interpreter, being a program written in C, will use the underlying hardware to do actual math. At some point you have to turn this stuff into binary computer numbers and do things with them. But when you're working at the level of Python, the variable a, although it represents a number, is not immediately something that the machine knows about. On the left-hand side, we have what the situation is in Go. I'm going to declare a variable a with initialized to the value of 2. And when I do that, a is just purely the name or address of a memory location in the machine. We're dealing directly with machine numbers in machine memory. There's no interpreter, there's no JVM. And so it's a bit different. And this is part of what gives Go its performance advantage. Because Go is taking the Go source, the compiler is generating machine code, the numbers are all represented in the machine representation, and so these operations are a lot faster. There's no abstraction involved in what is a number. So I'm going to look at basic integer types, and the most important thing I want to point out on this slide, the only thing you need to take away from this, is there's a default type for int, which is literally the word int. Now, there are several types of integers, and I'm not going to talk about them all. There are integers that have specific sizes, and they're signed or unsigned. And in a later segment, I'm going to talk about those and bitwise operators and some low-level stuff that most people don't need. For all practical purposes in Go, the numbers you're going to deal with, unless they're fractional numbers, are going to be ints. And if we write something like we did on the previous page, right? If I declare 2 and declare a and initialize it with 2, the number 2, a number like 2 in the text, is immediately going to be treated as an integer and therefore an int. And therefore a is going to be an int. Now, on almost all the machines you're ever going to work with at this point going forward, for like cloud software and laptops, they're going to be 64-bit machines. So an int is an 8-byte object, and it's so big you can literally count all the numbers, all the stars in the sky, as 64-bit int numbers. Now, if you're familiar with math, you're going to know that there's another kind of number. There's integers, and then there's what are real numbers. And as an extension of real numbers, there's complex numbers. I won't even talk about complex numbers anymore. Real numbers are numbers that represent fractions. So if I ask the question, how many students are in my class, that has to be an integer, because I can't have any half students, at least not bodily. But if I ask the question, what are the average number of students in my class, per week or something, then that's likely to be a floating point number, or it's a real number that we represent in floating point, because it's likely to be fractional. It could be 7.3 or something, and that's not an integer. Now, unfortunately, Go does not have a generic type for float, so they're sized. They're either float 32s or 64s. By default, they're float 64s. I'm not going to spend any real time talking about the difference, because we're not going to do any mathematical software. The one thing I do want to point out is it's really a bad practice to try to represent money using the built-in floating point types. And this is not just true of Go, it's pretty much true of any language. So floating point numbers are really designed to do scientific calculations. They don't do money very well. And one of the reasons why is that if we think about like 10 cents, well, that's a tenth of a dollar, $0.1. And when we represent that in floating point binary, it's a repeating fraction. It's a weird decimal, it's not, well, I can't say decimal, but it's a weird binary fraction that continues on. And so it's never completely accurate. The other problem we get into is rounding problems. If I take a dollar and I split it 3 ways, so if I divide by 3 in the floating point world, I would get 3 chunks of 33 cents, but that's only 99 cents with a penny left over. The right way to actually split up a dollar would be, somebody gets 33, somebody else gets 33, and the third person gets 34 cents. That's how you have to make change for a dollar. And you can't really do that easily in floating point without a bunch of logic, which is why you should use a package designed to do money and do that logic for you. So before I do anything more with basic types, I want to introduce how simple declarations are made, because I've already shown a couple examples of this. And I just want to explain something. So there's 2 ways to declare a variable. You can either use the var keyword. So here's an example where I've said var a int. A is going to be a variable of type int, because I gave it a type right there as part of the variable declaration. Now, if I look below that, I've got a couple more variables. And if I have several in a row, and I typically do this when there's at least 3, but I'll show it with 2 here on the slide, I can put them in parentheses and just have a variable group. And it's similar to what we saw with import statements. I can have import statements with a parenthesized list. But what's interesting here is I declared B and F and I didn't give them types explicitly. But Go can infer what the type is by looking at the number. So for B, I have the number 2. 2 is an int, therefore B is an int. For F, that initialized value is 2.01. Well, that's not an integer. So Go immediately assumes that's a float 64, and F then has the type of a float 64. So when I declare these variables, they have types. They have types at the point of declaration, because either I gave them a type explicitly, or I gave them a type implicitly because of the value that I used to initialize the variable. Now, there's another thing going on, and you've seen this also a few times, and you're going to see a lot of it, and that is within a function, okay, and only within a function, there's something called the short declaration operator. And it looks like this, right? A colon and an equal sign. In Go, it's not an assignment operator, it's called the short declaration operator. And its purpose is to declare a variable and give it a value at the same time and implicitly. So whatever that number is, in this case 2, we know what the type of 2 is, it's an int. So A is given the value of 2 and typed as an int right there. It's very convenient. So if you remember back, one of the ideas of Go was to make Go type safe in a static typing compiled way, but to make it easy to use as one of these dynamically typed languages like Python, where you just say, hey, A equals 2, and so A becomes a variable with the number 2 in it. Okay, so when I do this, when I just set this little C is declared as 2 or some expression, it doesn't have to be a literal. It could be an expression that calculates something, and whatever the result of that calculation is, or the result of the function call, the type of that becomes the type of the variable, and the value of that becomes the value of the variable. At this point, I want to show some examples, and so I'm going to go into the Go playground, and we're going to play. And the first thing I want to do is I want to show a couple examples of a very useful capability in Go. So I'm going to create a couple of variables, A and B, and what I want to do is I want to print them not only with their values, but I want to show what type they are, and this is a very handy way to do debugging. So it turns out there's a printf verb, and I think in a previous segment I used the term statement, but actually these percent things in printf statements and so on, they're really called verbs. So the %t verb, all right, is going to show the type of something. Oops. All right. And then %v is something that shows the value. And I can do this again with b. So when I run this, it's going to tell me the type of A and the value of A, and the type of B and the value of B. And they're not really surprising. A is an int, and B is a float 64. Okay, so this is a very easy way. I'm not only showing you how to declare things, but it's a very easy way if you're curious about what's going on in your program. But %v will print anything. It doesn't have to worry about what type it is. Now, I want to show you one more trick that I think is actually useful. And that is, in this print statement right here, like this first one, I had to give a twice because there's two verbs. There's the %t verb to show the type of the something, and the %t to show the value. And I'm also going to align these a little bit. So if I do that, if I give it a length, then it gives me the column size, and so these things are lined up a little bit nicer. But what I can do is I can put a different kind of number in front of the %v's, and what I'm doing with this 1 in brackets is I'm saying that it should reuse whatever the parameter 1 was. Now parameter 0 is the printf string, so the first parameter after that is the a or b. And so now I can get rid of these redundant a and b's, and when I run that, it's going to produce the same output. So if I need to get like the type and the value from a variable, I don't actually have to put it in twice, which is convenient if it's not a variable but an expression or some other complicated thing, or it's a function call that I don't want to call twice. I want to show one other thing, and that is I can assign, okay, the first question is, can I assign B to A? And the answer is, if I run that, it's going to say no. Okay, Go is a pretty strict language as far as types are concerned. I can't just assign a float to an int or an int to a float. I can't, and if we get into the sized ints, they're also distinct. I have to actually explicitly convert it. I have to do a typecast. What I can do then is I can say, take B, convert it to an int, and put that into A. Right? Fine. And now I'm going to print again, what is A? And of course, A is an int. And what is A's value? Well, it's 2. Now, let's suppose I changed B to be 3.1. Right? What's A's value going to be at the end of this? It's going to be 3. Right? When I go from a float to an int, the fractional part has to be removed. If I were to assign B is equal to float 64A again afterwards, and then I do the B print afterwards, okay, so the type of A and B can't change anymore. I can't convert A from an int to a float in the sense of changing the variable type. But when I change a value, I can convert the value back and forth. But now that I've taken A, I can convert it back to a float 64, I can assign it to B, but when that happens, B still has the value 3. Because once I truncated that fractional part, when I took 3.1 and converted it to 3 to put it into A, then I convert it back to a float to put it back into B, it still has the value 3 because the fractional part went away and it's never coming back. So I want to go back to the slides for a second now. I want to show there's some other basic types I want to talk about. The first of this is bool, and it's a Boolean type, and Boolean means it's true or false. And it's named after a guy named George Boole who invented Boolean logic. A long time ago in Fortran it was called logical, and that's what it is. It's a logical value, true or false. What's very important in Go is that there's no easy way to convert it back and forth to an integer. We have this notion in a bunch of languages, and this goes back at least to the C language, so it goes back like 50 years, that the value of 0 is logically the same as the value of false, and the value of true is like the value of 1, or any non-zero value is true, all right, or it's truthy if you want to look at it in that way. That's the way some languages call it. In Go, the Booleans and the integers are just separate things. So there's no way to actually convert a bool to an int or an int to a bool in the typecast way that I just showed for ints. You have to actually do something like, is A equal to 0? Okay, if that's the case, then it's true. Or is A not equal to 0? You have to have an actual expression, a logical or Boolean expression to do that. The second thing I want to talk about is the error type. Now, technically speaking, the error type isn't simple, but the part that's not simple about it, I want to defer. I want to treat it right now like a simple type and tell you that an error is either nil or it's not. And if it's not nil, then error somehow inside of it holds an error message that we can at least print out on the command line. We can print that out and see, oh, I got an error and this is the text of the error. And for the first few segments when we do some simple example programs, we're just going to treat error that way. I call a function, typically, let me write this, I'll call some function where I get error is equal to f of x, right? And then I'll just ask the question, is error nil? If it's nil, fx didn't fail. If it's non-nil, it's an error. The last thing I want to talk about are pointers. I'm going to treat them as a simple type because a pointer is just an address of something. Now, that actually opens a whole can of worms, and I'm going to defer that. I'm going to have another segment a little bit where I talk about pointers and what pointers are and how they work in Go, because folks coming from some languages like JavaScript are not going to be familiar with them. The important things about this, and there's two things I want to mention. One is a pointer is either nil or not. So a pointer references something, and if it has the value nil, which is a special value, it's literally written out as a constant, nil, then it doesn't point at anything, right? And that's sort of the difference between I have some values or I just don't have any kind of value at all. The other thing about it, and there's a number of languages where you can do funky things with pointers. C is a pretty good case. You can do very interesting things with pointers in C. They're also very dangerous. And so there's a package in Go called unsafe, which I'm not going to talk about anytime soon, that allows you to do some of that if you need to interface Go to the C language. The last thing I want to talk about with simple types is initialization. And it's very important because in Go, every variable is initialized at its point of declaration. Either you do it or Go will do it itself. There are no uninitialized variables in Go. And this is great. One of the worst production disasters I've ever seen in my career. It involved a very large telephone switch in Hawaii. It went down for like 13 hours. And the first cause, there were several things that happened to make that disaster. The first thing that happened was there was a program, part of the program had an uninitialized pointer, which picked up some random memory address. So Go prevents that kind of disaster. It gives it a zero value, and I put zero in quotes because the value, it is literally zero if it's an integer, but when you think about what is the zero value for a string, well, it's an empty string. It's a string that has no characters in it. Every type in Go can be reduced to these rules. It will be initialized to some zero value. So the last thing I want to talk about are constants. And constants in Go are kind of limited. The only things you can make a constant out of are numbers, booleans, and strings. Now there's a reason for that, and I want to give you the very short reason. And some people are going to complain, well, other languages let me make a constant structure or array or something. Go has a particular idea of what constant should mean, and in Go's meaning, it's immutable. Absolutely, completely immutable. It can never change. It's something that I could put into read-only memory that the hardware could prevent me from changing. And the reason Go does that has to do with concurrency. Go is a concurrent programming language from the get-go. And it's good to have constants that are immutable to be safe in a concurrent programming language. And again, I can't unpack all of that right now because we haven't even started concurrency. But there's very good logical reasons why Go limits constants to these things like numbers and strings because they are immutable. And the languages that allow, for example, a constant struct, they have pretty funky rules. If you look at C++, the constant tag is almost wishful thinking. It's like, I want you to treat this as const, and it is, except when it isn't. And that's not safe, and it's certainly not safe in a concurrent program. So again, Go has a very restrictive idea of what a constant is. And I've got a few examples here of const declarations. Basically it's like a variable, except it doesn't change. The type gets picked up from whatever you initialize the constant with. So if I initialize a with 1, it picks up the type int. Okay, I can initialize s with string, it picks up the type string. I'm allowed to do a few very limited things. I can do simple things like addition, and I can take the length of a string and make that a constant, so that's okay. I can't do more complicated string operations. That will fail. The compiler will just tell me you can't do that. So again, constants are very simple in Go, but they're still useful. So now I'm going to switch over to Replit, and I'm going to work through a small problem that will help illustrate some things about basic types. We're going to build a program that will calculate averages. So given the list of numbers, it will add them up, divide by the count of numbers, and show us the average. And it'll work whether we type the numbers on the command line or feed them in from a file. So the first thing I need to do we're going to take the very standard main.go here, but I'm going to need to add another import. And then I'm going to come down into my main function. So we're going to need a couple of variables. One to hold the sum, and one the total of numbers. And then we're going to create a for loop, and this will be a very simple for loop. It'll just go on until we tell it not to. All right, we're going to read in a value, so I need a place to put that. And now, let me make a couple of comments about what's going on here. The first is, notice these variables on lines 9 and 10, sum and n, and for that matter val on line 13. I don't need them to have any particular value. Well, actually I do. I need them to have the value 0. So they're going to have the default initialization. And there's a style that says, hey, if you're going to do the default initialization, then you might as well use the var keyword. So if you introduce a variable with var, you don't add an initializer to it in most cases. And then we'll use the short declaration operator when we want to initialize to a non-default value. We also have to use it if we're going to use the initialization in a if statement. Now, I haven't talked much about if statements, but this if statement has a declaration followed by a semicolon followed by a conditional expression. I don't have to write it this way. I could, in fact, put this on a line by itself, get rid of the semicolon, and it would have the same effect. Now, the other thing I want to point out here is what's going on here with and val. Well, in order to let the fScanLine function put something into val, I need to pass the address of val. In other words, the parameter fScanLine is going to be a pointer, not just a float, but a pointer to a float, and the address of operator is the ampersand. So the fScanLine function will get the pointer to the float, and you'll be able to use that to actually put a value in it for me. Now, the other thing that's going on here is we need to stop the program. And the easiest way to stop the program here is if we get to the end of file. And the end of file will be signaled as a special error. But at the moment, I'm going to keep things very simple. I don't care. If there's an error of any kind, whether it's end of file or an actual error, I'm just going to stop the program. So we'll break out of the for loop when I do that. Otherwise, I want to accumulate the value and increment the counter. And I'm using a couple things here very specifically. So the plus equals operator would be the same as saying sum equals sum plus val. All right, it's just shorter. So I can get rid of that extra thing and just say plus equals. And then I have an increment operator, which is the plus plus. Now, some languages allow you to put the plus plus before or after, and it has slightly different semantics. C is that way. In Go, it can only come afterwards, and more importantly, the increment operator is a statement. It has to be on a line by itself. It can't be part of some other expression. Okay, so what I'm doing here is I've got my accumulator. I've got the count of numbers I'm going to add up. I've got a place to put a value that I read in from the command line, so I'm going to read it. And if nothing went wrong, I'm going to sum it up. And so what I need to finally do at the bottom, I'm going to have to deal with a special case. What if there are no numbers? And so I'll do that by putting some logic here that says, well, if the count is 0, we're going to output a string that says no values. And what I also could do is actually fail the program. In other words, I could output an exit code that actually says, hey, this didn't work right. Otherwise, I'm just going to print out the average is. Now, it's not going to like this sum over n, because if we go back up here, we notice sum is a float, and n is an int. And in Go, these are separate types and they don't mix. There's no automatic conversion or promotion from integer to float, for example. So we're going to actually have to cast this to show our intent. And when I do that, then everybody's, well, if I add another parenthesis, when we do that, everybody's happy. Okay, so now I have my entire program, right? I've imported the two things that I need. Why do I need OS? Well, it's because I need to deal with standard in and standard error. Okay, I could just do print line and print on the console, but since I want to read from standard in, I have to get it, and that's where it comes from. Okay, so os.standardin is something I can read from, and I'm going to pass that to fscanline, which will scan a line of text ending with a new line and fill in whatever variables I've asked it to fill in if it can, in this case value. So it's assuming that there's going to be a number on the line by itself. If there's more than one number, it'll only read the first one and then basically skip and keep on going. So I'll read one number on a line by itself, add them up, but I also need, if I'm going to print an error, it's good style in a command line program to print those errors to the standard error output, which might be going to a different place than the normal standard output. So I've done that again. So those are, and then I needed OS because I wanted to be able to call the exit function. Okay, and of course otherwise I'm using the functions out of Fumpt, like Fumpt.println, and here fPrintLine simply says it's the same as println, but I'm going to tell you what output stream you're going to print on. So that's my program. If I run it, okay, it's not going to do anything. It's going to sit there waiting for input. So I'm going to type 3, 4, 5. Now, in order to get the program to stop, I need to signal end of input. And from the command line, that's Control D. And when I do that, the loop terminates and we get the average as 4. Okay, that's about what I expected. I gave it some simple numbers. Now, what's interesting is I can also put these numbers into a file. If I come over here, I can create a file. Okay, we'll just create a little file, nums.txt, and I'll put some numbers in it. Okay, and I believe it will just be saved automatically. So now if I go run, and I take that input from nums.txt, it just comes up with the average. Okay, so it read the file, and of course when it got to the end of the file that I read in by using the file redirection operator, okay, so I redirected nums into standard input, and then it read standard input as if it were from the console, got to the end of the file, found the end of file marker, and that's it. It gave me a result. I can also do it one other way. All right, I could cat nums, and that would have the same, yes, if I actually give it the right file name. Okay, and that has the same result. I took the file and I piped it into standard input instead of using redirection from a file. They all have the same thing. So the program will read from standard input wherever it came from, iterate around, and that'll be the end of it. Now, I haven't talked much about for loops, but this is a for loop that will simply run until it stops somehow. And the break statement here is a way of stopping it. And those are found in a number of other languages, so hopefully those are not very strange. And that's the whole of my program. So I've demonstrated using ints and floats. I've demonstrated the fact that you cannot convert between ints and floats accidentally. You have to deliberately cast, for example, an int to a float in order to use it in an expression with another float. And I've demonstrated a little bit about how to read from the command line and print output. Okay, so that got me through some basic types and declarations. We're now going to move on and talk about strings. They're a little more complicated. And after that, we'll talk about things like arrays, slices, and maps, which are a bit more complicated after that.